So it's my great pleasure to have here today Ginat, who did PhD at Tech in Israel. He won plenty of prizes, including the IU Best Thesis. And then he moved to do postdoc in Oxford as a Neville Piles Fellow. And he will give us the talk today. But of course, the most important thing is to share the office for almost a decade. So the stage is yours.
Thank you, Mo. And thanks for the invitation to come. So I will tell you today about galactic center dynamics. So this work is about resonant relaxation, really, and I'll explain what that is. And it's work that I've done in collaboration with Bence Kocic, Taras Panamarev, and Khagay Perez. Bence, from a postdoc here. Okay. Right. So probably you all know about this black hole that we have at the center of the Milky Way. And now we have even got a picture of it. And well, so the first thing you would notice about this black hole is that stars around this black hole, they behave just like planets around the sun. So they move in Keplerian orbits around the black hole. And if you want to understand what these stars do and sort of the long-term behavior of the stellar orbits in the galactic center, this is really just an interaction of Keplerian orbits. So it's also known now that there is disk of stars around the black hole. They're roughly 10 million years old, or a few million years old, and they're situated so they're between roughly, let's say, a few hundreds of a parsec and maybe half a parsec, and they are roughly a few thousand solar masses in total, and they orbit in some sort of disk, and so that's what we will be assuming for this talk. And then most of the questions that I will ask is what happens to this disk under perturbation. So suppose you have some other object which is not the disk. Can it excite perturbations in the disk? Can it warp the disk? Can it destroy the disk? Or maybe, it sort of becomes part of the disk. And the nice thing is that by observing this disk, you can learn about the history of what happened to it in the past, or and how much perturbation it's been subjected to. So the first thing I will be adding is a big perturber, one particle with a large mass, MP. And this large mass is such that it's much more massive than this particle mass, so much more massive than each of the stars, but much less massive than the mass of the total disk. And obviously everything is a lot less massive than the supermassive black hole. So you have this orbit, you have the angular momentum vector of that orbit, and because its mass is much smaller than the disk, the angular momentum vector is order some small number, which I call epsilon, times the disk angular momentum vector. And you put it at an inclined orbit, and you ask, okay, so what's going to happen? So the answer to what's going to happen is, by the end of this talk, you will know that this is what's going to happen. Eventually, it will merge with the disk. And so the question is, how does that happen? How quickly does it happen? And what are the processes, dynamical processes that give rise to this? So just to remind everyone here, I'm going to use a lot of Keplerian elements in this talk. In Keplerian elements, there are lots of angles, but today I will need just two angles. So there's the inclination of the orbit and the argument of the ascending node of the orbit. And these two angles together specify the direction of the angular momentum vector of a Keplerian orbit. And they are my angle action variables in phase space. So the action variable is cosine inclination, the angular variable is omega.
So you're assuming circular orbits or also, okay, but still you don't care about the argument periods.
Well, so I'll explain why I don't care about it, yeah, in a second. But before I do that, I'll just show you a simulation of what happens in the setup that I described. So this is the start of the system. All the disk particles, they're here. They have low eccentricities, and they have very low inclination. So that's why they're in a disk. Then you have argument of the ascending node in here, and argument of pericenter in here. And I want you to, when I press play, I want you to look mostly at this panel and at this panel.
Some embedded stellar cluster here.
Pardon?
You've written plumber at the top.
Yes, sorry. There is another component where this entire thing is immersed in a plumosphere. And I'll say something about the plumosphere, why it's immersed in a plumosphere in 2 slides.
And m dot is 250. What's that mean?
That's the mass of this thing. Okay, so I press play, and what you will already notice is that these things are doing something a bit strange. You know, they were spread out and sort of they become a line, and the inclinations got a bit excited. And so you see that after a very short time, these arguments of the ascending node, they sort of start to trail the argument of the ascending node of the perturber. And the inclinations go up, while the inclination of the perturber goes down. The eccentricities of these stars went up a little bit as well. But the important features I want to talk about today are these 2 panels. We see that the star sort of, the perturber sort of sinks into the disk while thickening it. And once it sank into the disk, I will argue that this alignment sort of stops being, that coherent anymore. So you have to wait a bit longer, but these sort of becomes thicker, and then the simulation is going to end soon. But
Is this n-body simulation?
this is an n-body simulation, yes. So that's done with Phi GPU, which has the potential to resolve the n-body interactions, but it can't do binaries. So I mean, it can do, but not in this setup. It can't. But yeah, it's this is a full n
particles do you have?
So here I think there are like 2,000 particles in the disk. This particle is live, but then the plumosphere is not live. Okay, so once the star is, so the perturber has sunk into the disk, this sort of thing has become a mess as well.
Does the color of a particle mean anything?
Yeah, it's proportional to its mass, but for us it doesn't. For now it doesn't matter. So I've drawn. I mean, so you can draw inclination as a function of time, and the inclination as a function of time goes down, and then it starts to wobble a bit after 10 million years. That's also been observed by other people, and today I'll try to explain how this happens. So the mechanism will be resonant relaxation, and the way this is done is as follows. So this is theory that has a lot to do with this institute, and so what you do is you say, well, the supermassive black hole dominates the potential, therefore the orbital periods of stars or the perturber are much shorter than all the energy or angular momentum exchange time scales, and they're much shorter than the time scale on which interesting things happen in this system. So we can orbit average all the stars around their ellipses. So we do that, we take a star, we smear it along its Keplerian orbit, and then we have essentially a system of rings or ellipses that are exchanging angular momentum they can't exchange energy anymore because we've sort of put that by hand with orbit average. But they can exchange angular momentum, so they can talk each other. And then the second component to this averaging is that because there is also a nuclear cluster in the galactic center, there's quite a rapid precession of pericenter for all of these orbits. So that means that you can take each ellipse and orbit average over the pericenter precession. So then you get an annulus, really. Each ellipse becomes an annulus between pericenter and apocenter. And this is why I don't care about argument of pericenter. Now, so while the first approximation was quite accurate, the second approximation is a bit less accurate, but it's okay, I think, for today at least. But I mean, you saw that things were happening in the previous video. You saw that while arguments of pericenter were precessing quite rapidly, maybe you noticed that there was a certain region where they were sort of in a resonance with the precession of the Perturber argument of pericenter, but I'm not going to talk about this today. But if you ignore if you ignore that, you can orbit average over the mean anomaly in the argument of pericenter. You get a theory of annuli or rings. And then these rings are described by angular momentum vector directions because they can't exchange angular momentum vector magnitudes anymore because you've orbit averaged over the angle that's conjugate to eccentricity. Okay, so that's called vector resonant relaxation. And the Hamiltonian for that is like this. So there's a sum over multiples. There's the same major axis ratio alpha to some multiple power, and the Legendre polynomial of the angle between the angular momentum part vector of star n and angular momentum vector of perturber p or star p or whatever. Okay, so you can split it like this. So you can have the disk self-interaction, and you can have the star, and you can have the disk plus perturber Hamiltonian. This has the same shape as this particle, but then if it's a very thin disk, you can do some tricks, and you can use Laplace-Lagrange theory to approximate this further and solve it sort of analytically. But yeah. So this is the Hamiltonian. It's a Hamiltonian of vectors or points on the sphere, and they interact with these Legendre polynomials. I put here sort of time scales. So the orbital period for our own Milky Way is very, very fast. There is the vector resonant relaxation time scale, which comes from this interaction for the disk. And then in sort of pale blue, you see the scalar resonant relaxation time scale is a bit longer. So that's when you allow them to exchange angular momentum magnitudes as well.
So
yeah.
Just to clarify, you said the degrees of freedom are points on a sphere because they're just directions of the
yes, but really they're points in a ball because the strength of each interaction does depend on the actual magnitude of angular momentum that each star has. So they're points on a sphere, but sort of the coupling coefficients know about the existence of
but that's not a degree of freedom because
that's not a degree of freedom because it's a fixed. Yes.
Okay.
So there are two degrees of freedom,
so
I and
like
omega.
Just a mass for the.
Yeah, it's a couple. Yeah. So there's I and omega, and that's it. These are my dynamical variables. Yeah. Okay. So this is the system. I want to ask if there are any questions about the way I set up. Okay. Good. There is a small parameter, right? Epsilon, which was the mass ratio. And how would I describe this alignment of the black hole with the disk? Well, I would expand, I would solve perturbatively in this epsilon, right? That's how I would do it. But there is another small parameter, which is the thickness of the disk, actually. So you have to do a double expansion, really. And it turns out that for that you might have that the disk thickness is smaller than your epsilon. And so interesting things might happen because you need to expand, you need to make sure that you expand in this and then in this correctly. So the point is that the disk is so thin that its self-interaction at the beginning, when it's thin, is less important than its interaction with the perturber, even though you have a tiny mass ratio. And that sort of is really why it's able to pull the perturber so quickly, pull it in so quickly. So it will turn out that there are 3 timescales in here. So even though I've sort of got rid of many timescales, there are still 3. There's the precession of the angular momentum vector of the perturber around the angular momentum vector of the disk. So that has this frequency. And then there is another timescale I'll talk about in a moment. And then there's the timescale where the whole thing happens. That's the alignment timescale for when the perturber will finally align with the disk. It turns out that it has this dependence on disk mass and perturber mass, and it's inversely proportional to the to this function of the perturber inclination. I should say that if you assumed that this process was just Chandrasekhar dynamical friction, you would get that this timescale is the square of this thing with a different trigonometric function. And when you plug that into the simulation, you get hundreds of times too slow. So it can't be Chandrasekhar, it's got to be this resonant effect, where you have the square root. This time,
This is an empirical fit, or this is from BRR twiddle arguments, or
this thing,
yeah.
This I can calculate. The Chandrasekhar one you can also calculate.
But where does this? Is this a theoretical result, or
This is a theoretical result
coming from VRR?
coming from VRR. Yes, and then this time scale is the time scale. I can hopefully explain why this time scale, the yellow one, is the time scale it takes the arguments of ascending node to align each other with that of the perturber, as you've seen in the video. And when you plot them, they turn out like this. So the fastest time scale by far is the yellow one. And then, a few million years, you have the precession of the angular momentum vector of the perturber around that of the disk. And finally, you have the full, what I call dynamical friction time scale.
You just say it's not dynamical friction?
It's not Chandrasekhar dynamical friction. It is a dynamical friction because it's a torque that the perturber excites a response, and the response pulls down the perturber in some way. We call it resonant dynamical friction because it's not Chandrasekhar dynamical friction. So if you plug in the formula that Chandrasekhar had, you would get the wrong result. Yes, is that clearer?
So the amplitude of L doesn't change.
No.
Okay. I just find the
directions
friction terminology counterintuitive because you're not changing the
So
magnitude.
you have an action variable cos I.
Yeah.
And that action variable can change. So in that sense, it's a dynamical friction.
So which resonances play a dominant role?
Well, so the reason I call this resonance is because this is a Keplerian system where you have lots of resonances, right? So because it's a and because it comes from resonant relaxation, right? So the word resonant in this term, in this name is just to show, to say that this is a resonant relaxation phenomenon. So it's all the Keplerian, degeneracies, basically. Okay, so how do we do it? Well, we solve in epsilon, and when you set epsilon to 0, you get that the perturber angular momentum just processes around the disk angular momentum with a constant frequency, and you have to believe me, and this is what comes out. Good. I should say that this is what comes out when you have a perturber, so and it's independent of epsilon. right? Good. At first order, you plug in the zeroth order solution and you get this equation of motion. So remember, omega is argument of the ascending node. B is some coefficient that you get from this Hamiltonian with the Legendre polynomial that I showed you. And then there's cosine of the difference in argument of ascending nodes. But I just told you that B is the, 1 over B, because B has units of frequency, is the shortest time scale in the system. So B is much bigger than this time scale. So the time scale for this thing to process is much longer than this coefficient. And when you have such an equation, really what comes out is that the solution to this equation is cosine equals this. So actually, when you solve this equation where this thing is 1 over epsilon, right? Essentially 1 over small number, so very big number, then the solution is omega n equals omega p plus pi over 2. That's what you get. And this is a picture from the simulation. It's a bit difficult to see in this picture, but you can you have the Perturber orbit and you have the stars on overlapping semi-major axes. So the green ones are stars with semi-major axes that are outside of the apocenter of the Perturber. These have long dynamical times, but the orange and blue ones are the ones which are inside the semi-major, the orbit of the Perturber. And here you might be able to see them trailing it. But when I plot the actual results, so here you have an n-body result. So the green stars, sort of their omegas are all over the place. The blue and the orange stars have arranged themselves in such a way that they're roughly 90 degrees above the omega of the Perturber. So
Can you do this in a way that's not like epsilon and epsilon squared and so on? Like physically, have you found some resonant trapping process by which these things align in 90 degrees? It's misaligned, the nodes are misaligned by 90 degrees.
I would say that the honest answer to your question is no. I can only do it like I've done it. And I would say that that's probably an open question to find.
Can I recast your equations of motion as a Hamiltonian and then swap the phase space of that Hamiltonian and it'll have a fixed point?
Well, it is supposed to be a Hamiltonian, and then you can plot it. And I don't know what you'll see because
like a cosine type thing where you have fixed
but
points.
it will probably sort of have a fixed point where they're 90 degrees away. But that's a nice figure to make, I guess. And then, yeah, so this is the analytical prediction of the equations of motion. So, so you get this 90-degree alignment, okay? And then I want to say that how long does this persist? So you have the Perturber omega, you have the green, blue and orange omegas, and the green ones are, remember, they're sort of outside, so nothing, we don't care about them. But the blue ones are overlapping, and so the orange ones, and you see that there's this, so here you see that they have a big variance at the beginning because we've sampled the angles uniformly, and then the variance shrinks and they get aligned, and at some point they stop being aligned, and when they stop being aligned is exactly where the Perturbers enter the disk. So you don't have this hierarchy of two small parameters. Okay, now the last thing to solve in this perturbative expansion is the equation of motion for the inclination of the perturber. So you can do that. That looks a bit complicated, but what it turns out to be is a very simple equation where there's this resonant dynamical friction timescale, which I've calculated. So that's just the coefficient that appears, and it's proportional to time. And time here is measured from the time when the disk was very thin. So you can see that this equation tells you that, well, I will just go down. I plotted n-body and analytical here, and you see that you get the correct timescales. You don't get the oscillations in the analytical solution, but that's just by, I guess, fiat, because the oscillations are very well understood. If you have the perturber entering the disk, so once it's sort of on a similar inclination to the disk, you can use no known Laplace-Lagrange theory to explain these oscillations, and they will continue forever. These oscillations.
Can you give some information? Why does it go with the resonant time squared rather than time?
Well, okay. So the intuition comes from it has to be proportional to time, and this has units of 1 over time. This is units of time. So you need the coefficient with units. No. So the real intuition, right, is why is it proportional to t to the power of 1 in here, right? Because the moment I've explained that, I've answered your question, right? And the reason is that it turns out that this is the equation, and you have a difference between the angle at time t and the angle initially. That's how it enters the equations, and so this, for generic system, this is going to be linear in time at early times, right? So the reason so this has to be linear in time, and therefore the coefficient has to have units of time squared.
But at late times it will be oscillating in time.
At late times it will be different, right? And that's why this equation is an approximation. I mean, to show the figure that I've plotted, I use this equation rather than.
Sorry, I don't see how this becomes something linear in time. Maybe it's obvious.
At early times, this difference is going to be proportional to I n dot times t, right?
Squared.
Yeah.
Well, no. So
Oh, I see. It doesn't start from 0 necessarily.
it does not start
Yeah,
from
okay.
0.
I see. Okay.
Yeah. Sorry, it starts from close to 0, but yeah.
But but then it's a small. Okay.
Yeah,
If it
it's
starts
a
from
small.
0, if it starts from 0, then it doesn't start linear in time, right?
Yeah, but it doesn't start from 0. And there is this b that is a very large number to cancel this, right? So there's a linear in time piece with a small coefficient, and then there's this b which is very large, so it cancels the small
I see.
coefficient. So I would say the limit where the disk is 0 thickness is a singular limit, so you shouldn't solve that. You should put like 10⁻⁵ or something, and then it works. Yeah. Okay. So that's the equation. And then, so what's the condition for alignment? So I've already hinted at that. The condition for alignment is that the thickness of the disk times the mass of the disk is smaller than Perturber inclination times mass of Perturber. And you see that because we've run lots of simulations with different configurations, so we can make the nuclear cluster live, we can change eccentricities, we can change masses. You see this alignment happening. Or lots of configurations, you can make the Perturber very eccentric. You can, you can change its mass. You can do lots of things. You can change this, some mass of the disk. The only time where you don't see it is when you have a thick disk. And that's exactly the reason, the condition that I've given. So you see it all the time except when you have a thick disk. Now I want to talk about the opposite limit. So what happens if the Perturber is more massive than the disk? Can we see something else? And the answer is yes, we can see something else. And it could even destroy the disk. So how do you do that? Well, you can write down. Can you write down some criterion for when the Perturber will be able to destroy the disk? And the answer is yes, but you have to do it all in angular momentum space. And the idea is as follows. So you look at the star orbiting, processing around its own disk angular momentum, and then you put in the torque from the Perturber, and you ask, well, is this torque from the Perturber bigger or smaller than the torque difference that the star feels along its orbit around its disk angular momentum? So this is a very, very close analog to what you all know about tidal forces, right? So how do I know if a small system can be ripped apart in real space by a Perturber? Well, the answer is I look at the tidal force of the Perturber and compare it to the force that the small system uses to hold itself intact. So this is the same thing, but in angular momentum. And I should stress that you can have, you can have a pair of stars in angular momentum space that are going to process around each other, which is like a model for a disk. But these stars don't have to be binary in real space, right? They can be on completely other different sides of the galactic center, still process around each other in angular momentum space. And so you can have, so this is what they're going to do. If there's no perturber, if there is a perturber, there are two possibilities. Either they continue to process around each other, but they will also together move around the perturber, or the perturber will just destroy them and they will be decoupled. So this is work that Taras was leading, and we considered the four-body problem. You have supermassive black hole, you have a perturber, which is an IMB8, and you have the pair of stars. And then we got this criterion, so the relative torque along its sort of direction, because that's the only way to change angular momentum, and you compare it to the torque from the disk itself. And so what we've plotted, what's plotted here is the two parts of this inequality. And the inequality says when red is bigger than blue, the angular momentum pair should be destroyed. And the bottom part is a simulation in N-ring. So N-ring means you take those equations of motion with the Legendre polynomials and you integrate them numerically. And what you see is that, so red is only very, very slightly larger than blue. Nothing happens. Red is bigger than blue. Nothing happens when it's smaller, but lots of, but the angle between the pair becomes arbitrarily large when the red is bigger than the blue. So that's good. It validates the idea. Simple tidal criterion works. There's another setup where we've changed the same major axis ratio between the IMBH and the pair. So before you had one bump, because this was a small same major axis ratio, and you get a one bump if, and in the Legendre series expansion converges very quickly, so you really are only dominated by quadrupole. That's why you have one peak. But you can have two peaks, and again, red is smaller than blue. They remain stuck together. Red is bigger than blue. They don't, and exactly what the red is bigger than blue. So we have an efficient criterion for deciding when a perturber will destroy a disk. And I think that's important because we see a disk in our own galactic center, which is intact up to about 0.4 parsecs. And then there is a different orientation of another disk, basically a counterclockwise disk at larger radii.
What percent of those perturbers expected to be?
That depends, because these intermediate mass black holes at the galactic center have not been seen, as far as I know. There's an object called IRS-13, which is debated whether it's an intermediate mass black hole or not. But if you believe the theory where the nuclear cluster was born as, there were globular clusters that were sinking into the galactic center, and together you had lots of them, and together they built up the nuclear stellar cluster. And if you believe the idea that globular clusters, so that a fraction of globular clusters host an intermediate mass black hole at the center, then you should have lots of them coming in periodically. Every time a globular cluster comes in, it will bring its own IMBH with it. But honestly, it's an open question because we haven't seen IMBHs in the Milky Way galactic center. And because of what I've told you before, right? Even if you do bring an IMBH in, it's gonna align itself with the disk. And the moment it's inside the disk, it will have a strong real dynamical friction and go down in orbit in radius until it sort of merges with the supermassive black hole. So yeah, I mean, open question, really.
So can you give us some numbers, some time scales for these various processes?
Yeah, it's a few million. So for the Milky Way masses, it's a few million years. So maybe I'll go back.
Okay, it's here.
To here. So this is the size of the disk, let's say around 0.1 parsec. Orbital time is a few thousand years. Resonant relaxation time, so everything I've been talking about, a few million years. Everything else, much slower. Any other time scale? So this tau dynamical friction I've been talking about, for an IMBH of, let's say, a few thousand solar masses, it's comparable to this. So it scales with the square root of the, so it scales with the geometric mean of IMBH mass and disk mass. Our own disk is a few thousand solar masses, maybe 10,000. So it's the VRR, it's the vector resonant relaxation timescale multiplied by the square root of mass ratio between perturber and disk, I would say. And does this trigonometric function of inclination as well, right?
It seems like the relativity precision time can be comparable to the resonant relaxation time at some
at the inner edge of the disk. But that's excellent for me because that's another source of precession of argument of pericenter. So that's another justification for neglecting the, you know. It's very maybe it sort of causes trouble for people for other studies, but for this study it's great because it gives you further justification.
But when the timescales match, then it doesn't justify the average. Because in the inner edge of the disk, your timescale of relativistic precision can be the same.
Well, I mean, a factor of a few, that's right. But it's just another source of precession, basically, of pericenter. That's what I'm saying. All the simulations that I've shown so far and everything is GR-free. I mean, it's completely Newtonian, but so our source of mass precession is just a Plummer sphere or a live nuclear cluster. But you're right that you need to account for this GR precession at the inner side of the disk. Okay. Right. Okay. So let's see. So this perturber can be something else other than IMBH. It can be the actual nuclear cluster, but that's complicated because the torque due to the nuclear cluster that I've put in that formula is not a coherent thing. The nuclear cluster is a composite object. Each star has a different angular momentum, so you need to calculate this with more care. So what I will talk about today, because I have, I think, a few more minutes left, is what if you have a fuzzy dark matter core at the center of the Milky Way, and what does that do in terms of resonant relaxation as a perturber? So, okay, so IMBH we've discussed. I haven't told you about what whether an IMBH can reproduce all the features of our own disk, because that will be positive statement rather than a negative statement. It's much easier to say the disk exists, therefore a perturber couldn't have completely destroyed it, right? So that's why I'm going to talk about this. So just very briefly about fuzzy dark matter. It's a dark matter candidate with a very, very low mass. I'm going to talk about order of 10 to minus 20 electron volts. And the theory, and it's a boson, so it can form a Bose-Einstein condensate and a very dense core at the center of a dark matter halo. Now, I will be assuming that, so these relations, right, the radius of the core as a function of dark matter particle and mass of the core as a function of dark matter particle mass and galaxy mass have been verified numerically and also argued for analytically in some cases. But I will just be asking what happens if a fuzzy dark matter core is formed such that it satisfies these relations. So if that happens, then I can plot timescales. I can plot a function as a function of particle mass. I can plot the gravitational radius of this fuzzy dark matter core, which you put in a supermassive black hole at the center of that core, you form a hydrogen atom, right? Because you have something that satisfies the Schrödinger equation, and the potential is dominated by the supermassive black hole. So the radius of this hydrogen atom in parsec is plotted in blue, and the frequency of this hydrogen atom is plotted in purple. And well, you see that in this mass range, there are of the order of the size of our Milky Way disk. And the question is, can we have this fuzzy dark matter gravitational atom perturb the disk, and can it destroy the disk? Maybe. And can this be used to place constraints on the existence of such a thing? So the answer is, well, possibly. So we have a gravitational potential due to the gravitational atom, right? So you have the fuzzy dark matter field, square it to get density. Here's the gravitational potential. You put a star at position X, and you calculate what VRR effect that would do. So you have to take this, and you have to orbit average it twice over the mean anomaly of the star and the argument of the pericenter of the star. And then the nice thing is that this omega comes out to be much faster than the vector resonant relaxation timescale by sort of luck. So you can also average over these oscillations of the gravitational atom. And you can do this, and the VRR potential that you get is there's a coefficient, and it's a sum of spherical harmonics, and there's a spherical harmonic of the angular momentum vector of the star and the angular momentum vector direction of the fuzzy dark matter. Now, I should say, if the gravitational atom is completely symmetric, spherically symmetric, there is nothing here. So this GLM come out 0. But so there's a parameter that would describe how spherically asymmetric it is. So the amplitude of the JLMs, basically.
So which what function are you using?
So far, it's anything you want.
Yeah, sure. Okay.
And then in the next slide, it's going to be a very, very simple one.
Okay, let's see.
But so far, it's anything you want. And I should say that if you average over the frequency of the gravitational atom, so these alphas, they oscillate in time generically, then you reduce a YLM to a Legendre polynomial. And again, you get exactly the same Hamiltonian, so you can do exactly the same physics. Now here I've defined this parameter, alpha, which is how much rotating mass you have. So this describes, out of let's say you have a fuzzy dark matter core, out of the fuzzy dark, which satisfies the core halo relations that I put before. Out of this expected mass, how much actual mass do you have in that core, and how much of it is in the non-rotating, is in the L not equal to 0 part. So that's a parameter, and if it's 0, then you can say nothing. But if it's non-zero, you can say something.
Why would it not be 0?
Because in the Milky Way center, everything has angular momentum. Everything is rotating, and we are a disk galaxy. So why should it be 0?
Well, but I don't know about the dark matter halo. I mean, everything, the stars are rotating.
So the dark matter halo, I think, has some spin parameter, which is, I don't know, whatever it is, 0.05 or something. So it has some non-zero angular momentum. It's not very large, I agree with you. Alpha is not going to be 1 or something, right? But I mean, it's a free parameter, right? So it can be 0 and it can be non-zero. That's all, I mean.
Well, I would expect the soliton to be approximately spherically symmetric. And then if you want to decompose it in eigenstates around the black hole, then sure, you'll get some coefficients around all eigenstates, and the only non-negligible ones will be the spherical symmetric ones. That's what I'm going to say.
Well, but they're gonna go away, right? Because they're accreted into the black hole on a very fast
It
time
depends
scale.
it depends on the mass. If the mass is very light, the accretion time scale is very long.
So for the masses that I am talking about here, so where the ball radius is as a few is of order of this, and our own Milky Way mass, they will be. I think if I've plugged into the correct formula, they will. The L equals 0 bit will be.
Okay, let's say you remove L equals 0.
Yeah.
And then you have L equals 1.
Yes.
But if you have a superposition of all L equals 1, say it's still spherically symmetric.
But that's going to give you a non-zero potential. Right? Because of the, right? So each one of them is going to give it a different YLM and so.
But the sum of them will be, a spherical symmetric potential. So how does that give vector resonant relaxation?
Well, the sum, I mean, if you have L equals 1 components, each one will give you a different YLM. So why should the sum be a spherically symmetric potential?
Well, if I take a superposition of 2 on 1, 2 on 0, 2 on minus 1.
Yeah. And you square that, then there's no interference. You're saying between.
Yeah, I get something that is spherically symmetric.
Okay, we have to work this out. Because
Yeah.
I mean, if I've done the math correctly, I don't get 0. Okay. Yeah. Okay. Okay. Well.
Still have some time because we have plenty of questions.
So I should. How much time do I have?
Say 5 minutes.
5 minutes. Okay. Yeah. Okay. So I'll just say that for the purposes of drawing a plot, I'm assuming this, which is the simplest thing you can, which is non-spherically symmetric you can have, and then I can plug in the formula and get some very, very simple things. And then I can write down the stability criterion from above, so you can calculate the torque due to the fuzzy dark matter distribution. You can calculate the torque difference on the disk, and here I've just summed up all the multiples for a disk, and then you get an inequality for this case. And that reduces, for this wave function, it reduces to this, and there's alpha, which is a free parameter here. And so you can rule out certain values of alpha and join certain values of alpha and certain values of the mass, if you believe in that wave function. But for other wave functions, this is going to change. For other profiles, this is going to change. And obviously, for low values of alpha, then you get nothing. So if it's very spherically symmetric, as you're saying, then you don't rule out, you don't exclude it.
Doesn't this also depend on the total mass
of
the atom?
So the total mass of the atom goes into alpha, right? Because alpha, I was saying alpha is the ratio between the actual mass divided by the mass that you get from this core-halo relation, right? So assuming you know the halo, you plug into the core-halo relation, you get so you get what I call MA expected, right? Which is a number that you sort of calculate. And then the actual mass will depend both on how much of it is spherically symmetric and on how much actually exists, right? Relative to how much you would expect.
And do you remember, sorry for my questions.
No, it's
Do you
fine.
remember that how much is this MA expected?
I don't, sorry.
Okay.
But well, it should be less than the black hole mass, than Sagittarius.
Way less than the black hole.
Yes. But the disk mass is like a few thousand, right? So you can play with this hierarchy. Yeah. Okay. Yeah. So that's my summary. Resonant relaxation is interesting. It controls the dynamics of our own Milky Way disk. And if you want to understand where it comes from, how it looks like, and what things do to it, then this is the theory you should write down. I've described what happens when you have a perturber with a very small mass ratio compared with the disk, how it sinks in. And then I told you how you can break a disk with a perturber, and also maybe more exotically, what if this perturber is a quasi-dark matter gravitational atom around black hole. Thank you very much.
Thank you, Bob, for the great talk. Any more questions? Then I will ask one, maybe related to the first, but what
Yeah.
happens if you have something like that rescaled down for protoplanetary disk?
You get the same physics, I think. You get the same phenomenon.
Okay.
And I think I've seen a paper by Affiliation et al. Who have looked at this in a protoplanetary disk, and they found a very similar sort of alignment phenomenon. And then so there they had a planet and a planetesimal disk, and they found an alignment between the planet and the planetesimals. So it's the same. It's the same. If you have a cold disk, right, and if you satisfy these conditions for alignments, then it's the same physics.
More questions? What one?
So when you said that the Chandrasekhar dynamical friction is much weaker than the resonant relaxation, and then I asked the question, what resonance is dominant? You said that there are actually many resonances with this regenerative current systems, a continuity of resonances, let's say, or very dense resonances. Then that sort of tells me that you should be able to get something like the Chandrasekhar because you have many resonances, and that's how you get from the LDK torque.
Okay.
So
I'll have to clarify what I said before. By Chandrasekhar, I really meant you take the original formula for Chandrasekhar dynamical friction, and you know which was derived for a homogeneous medium and the particle going on a straight line velocity forever and ever. That formula, if you use that for describing an alignment, will give you something very slow. But
what Coulomb logarithm did you take?
like number log n or something. Oh, I mean, I think it must have been log n, or I don't know. But the point is that the dependence, there is actually a figure that I didn't show, but the dependence on the mass of the perturber and on the disk mass will be different. It will be m black hole squared over m disk m perturber, and we've checked that. So we've done dynamical friction. So we've done the same thing with simulations with different IMBH mass to see how the time it takes to go down scales with the IMBH mass, and this square root is satisfied by the simulation.
An intuition for why you get the square root?
Well, it really comes from most question before, where you had something that is, so you don't have an autonomous equation really for the inclination as a function of time. And therefore there's a coefficient, the coefficient in the equation, which is proportional to the perturber mass, right? Comes, I mean, that's not going to have units of time. It's going to have units of time to the power of 2. So to get the time scale, you have to square root, and that's where there's a difference. Whereas in Chandrasekhar, you do have an autonomous equation, and therefore the coefficient will really have just units of time, and that's where it comes. That's where the difference comes from. I think it's quite a subtle one, but yeah. But the square root is really is satisfied by simulation, so it can't be another phenomenon. So it can't be. Yeah, so it has to come from that thing.
So this is not resonant friction in the sense of a sort of load LBK thing, right? Resonant here is a bad word. It should have been called closed order relaxation, closed orbit relaxation, or commensurable relaxation, or something.
Well, I mean, I didn't come up with.
No, I know. That's what's leading that's what's misleading about it.
Yeah.
It's a completely different physical effect to like an LBK. So you won't just be able to stack all these high order effects together and recover Chandrasekhar and something. It's a totally different scenario. It's just the words are the same.
Well, it's just because these talks, they sort of, well, these orbits, they are talking themselves in a coherent manner along this so when the star is going along the annulus and then precessing, it remains like coherent, so.
It's not the same as when a dwarf galaxy falls into a halo and then the high end limit of that is Champs taken. It's a totally different scenario.
Okay. Any more questions?
I mean, I'd be very happy.
Entropy all that.
I'd be very happy to see a derivation, if you can. Well, I'd be very happy to see a connection between this and LBK, if you can find,
The derivation of that is all assuming non-commensurable orbits.
well,
You have to average up, you have to change coordinates to fast
Yeah.
and slow, you have to
No,
have fast up.
I know, but there are Fouveray papers where sort of generalize it and
Yeah.
then they become a bit more they become more complicated what I've said here, so.
And basically just saying that you cannot take the classic LBK formula, plug something in and recover this. You'll
No,
never-
sure, yeah.
Okay, last questions? Okay, then we'll thank Paul again. He will stay here for the rest of the week, so feel free to perturb him.